Hello, Chem 1A. This is Chapter 10, Lecture Video 5, and we're going to be discussing formal charge. Formal charge is rather important, specifically when we have multiple possible Lewis structures that we could draw. For instance, we'll get into this on the next slide a little bit, but you can actually draw CO2 two different ways. You can draw CO2 like this, and this is the one I've shown you on previous lectures videos. But another way to draw this is like this. And they're not technically resonance structures because they're not energetically equivalent structures. So there are two possible ways to draw it, and only one is technically going to be the best answer. And that's going to be this one, as we'll see on the next slide. Now, how do we determine that? How do we determine that CO2 probably has two double bonds as opposed to one triple bond and one single bond? The answer actually lies with formal charge. Formal charge allows us to determine how stable the Lewis structures we draw are. Now, as a general statement, when we're looking at formal charge, and I'll show you how to calculate it in just a second, we want to look for the lowest amount of formal charge. Now, formal charge can be either positive or negative. And when I say the smallest amount, I don't mean either of these. Smallest amount means closest to 0 in this case. So -1 is better than -2. +1 and -1 are pretty much equally bad. They're not great, they're not horrible, but there's no difference between a -1 formal charge and a +1 formal charge. They're both not really great. The next bit about formal charge is when we calculate it, we want the negative charges to be on the elements that have the largest electronegativity, the trend that we just talked about on the last lecture video. So the opposite of this statement is also true. We want the positive charge to be on atom with lowest electronegativity, right? En for short. So these are some rules. Now let's talk about how to calculate it. We'll get into more rules in terms of determining how to switch between the most stable based on this. How we calculate it is basically the top equation is what you're going to see in your textbook. So that one's going to be your textbook's definition, which is for each atom in the structure, we're going to take the valence electrons of that atom, subtract all the lone pair electrons around that atom in the Lewis structure, and then subtract half the bonding electrons. Remember that a single bond contains two bonding electrons. Now, that's a great way to do it, and if you like that way, by all means memorize that equation and use it that way. I prefer the more visual method. I'm more of a visual learner, so I like thinking about formal charge as number of valence electrons minus number of dots and number of sticks around the atom. For instance, if we're looking at this oxygen here, right, there are 4 dots around that oxygen, right? We can see them. I'll highlight them in green. 1, 2, 3, 4 dots. And there are 2 sticks. 1, 2 sticks. All right, so I know oxygen has 6 valence electrons, and I know there are 4 dots and 2 sticks, which gives me a 0 formal charge on this oxygen, right? And so that's how I can kind of calculate it. Now, we're going to draw the structure of these next 3 structures to calculate formal charge for every atom in the structure. And we're going to do that on the next slide because there's just not enough room on this slide to do it. So let's look at CO2. All right, CO2, we've only ever shown it, or I've only ever shown it drawn like this if we look at its Lewis structure. But there's actually 2 ways to draw CO2. You can draw it this way. That is totally correct. And it's actually, this is the best answer. But you could also draw CO2 like this and not violate the octet rule or how many electrons there are in the structure. Both of these are possible Lewis structures for CO2. But if we look at formal charge, remember, we don't want any formal charges if we can help it. If we look at calculating some formal charges here, this formal charge, remember, is equal to valence electrons. Well, oxygen has 6 valence electrons. Minus, again, you can do lone pairs. Well, there are 4 lone pairs around this oxygen atom in this structure, minus half the bonding electrons. Well, there's 4 bonding electrons here, times 1/2 gives me 2. Now I like the other version, right? Dots and sticks. So each one of these dots counts. So 1 dot, 2 dots, 3 dots, 4 dots around the oxygen, minus sticks. Hey, there are 2 sticks there, minus that. This gives me a 0 as my formal charge here. Carbon, we can do the same thing, right? Formal charge, again, is equal to valence electrons minus dots minus sticks. No dots around this. Carbon has 4 valence electrons. 4 sticks around it, too. 0 for its formal charge. And this guy's 0, too. You just can trust me on that. It's starting to look exactly like this one. But down here, if we calculate the formal charge of this oxygen, it's a little different. Formal charge is equal to 6 still. That's how many valence electrons oxygen has. Minus 6 dots and 1 stick. Or in other words, a -1 formal charge here. This oxygen here is going to be different as well. We have 6 minus 6 dots. Ooh, I did this wrong. This shouldn't be here like that. There we go. Sorry. That structure was drawn wrong. So it should be 6 valence electrons minus 2 dots and 3 sticks, or in other words, a +1 formal charge. Now, this guy has a 0 formal charge if you calculate it. Which of these Lewis structures is better? Well, we have formal charges on this one. We have no formal charges on this one. This is our best Lewis structure out of these two. And that's why I've always drawn it with 2 double bonds as opposed to 1 single bond and 1 triple bond. So let's look at CH4. There's actually only one way to draw CH4 because hydrogen is only ever happy with 1 single bond attaching to it. And this is our Lewis structure. Again, if we look at carbon's formal charge, we have 4 valence electrons minus dots minus sticks. Well, no dots, 4 sticks, 0. All these hydrogens are going to have the same one because they all look identical. We have 1 valence electron minus 0 dots minus 1 stick. All these guys have 0 formal charge. The last one was phosphate, I think. So we have PO4 3-. If we draw this guy's Lewis structure, you can draw it with our 4 oxygens all attached to the phosphorus. I'm going to erase my little arrow here, give myself some more room. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And this is done. All these oxygens have a formal charge of 6 valence electrons minus 6 dots minus 1 stick, -1. And there's a lot of pattern recognition here. Like, for instance, I notice all these oxygens look the same. They all have 3 lone pairs and 1 bond. So they're all going to have the same formal charge. So phosphorus is going to be a formal charge of, well, we have 5 valence electrons in phosphorus, and we have we have no lone pairs, and we have 4 sticks. So this gives me a +1. So this is giving you an idea of how to calculate all these formal charges. Okay, so the last bit here is just to talk about the different things that you need to kind of understand about formal charge in order to check and see if we've drawn the most stable Lewis structure that we can draw. Now, one of the things that is just a default statement is that when you add up all the formal charges on your molecule, they need to add up to 0 if it's a neutral molecule, and they need to add up to the charge on the ion if it's an ion and has an overall charge. This is not negotiable. This doesn't tell us that it's more stable or anything. This just is straight up a default statement. And if it's not true, if your formal charges don't add up to 0 for neutral stuff and don't add up to the charge for charged stuff, then one of two things is messed up. Either you miscalculated one of the formal charges or you drew the Lewis structure wrong. So you can kind of figure that out there. When we want the most stable and most plausible Lewis structure, we're looking for the one with 0 formal charge on every atom in the structure. So if we remember from the last slide, methane, CH4, right? None of the atoms in that structure had a formal charge. That was the best structure for that molecule. In fact, you can't draw that one without having 0 on all the atoms. Sometimes it's not possible, though. Sometimes you have to have formal charge on your structure. When formal charges are required, we want them to be as small as possible. The smaller your formal charges overall, the better. And we want the negative charges to appear on the most electronegative elements in the molecule, and the positive charges to appear on the least electronegative elements in the molecule. Finally, generally, the best Lewis structure that you're going to get is where you get a 0 formal charge on the central atom. So if you can get 0 as your formal charge on the central atom, most of the time that's going to be the best structure you can get. Not always, but most of the time. All right, so if you have any questions, please don't hesitate to contact me as always. Oh, sorry. Also, one last bit. I lost a bullet point. We don't want negatives next to each other, right? So for instance, if we have molecule X, Y, this has a -1 formal charge and this has a -1 formal charge, that's real bad news. We either want Y to be 0 or +1 at the best, right? So they definitely don't want 2 charges that are the same sign right next to each other. All right, so as always, if you have any questions, just let me know.